Yes. Yes. Okay. Thank you, Andrea Tidello, for this introduction. Yeah, and sorry for the long title. This just came up. The last question, I think, was a good introduction to this presentation, since we will also see a little bit or focus a little bit on crack location, in this case on hollow sections which are related to motorcycle handlebars, also of the project Multifun, which was the framework of the last presentation as well. And this work, just as one word in ahead, is a collaborative work together with ADAC Engineering, which are responsible for the design of this motorcycle handlebar, and the LKR center in Austria, who are manufacturing the WAAM specimens for this work. So as I already introduced, motivation is such a motorcycle handlebar, which will deal as a demonstrator in the Multifun project, and from this we derived some specimens to perform a fatigue assessment on this handlebar section. The Multifun project itself focuses on multifunctional materials and multi-material combinations, so it is enabling multifunctionality performance through multi-material additive manufacturing. So you can see here, for example, one component combining two metallic materials, and on the left side there's the WAAM process itself for manufacturing a see-through A-pillar, which also includes cooling channels and so on. So this is the framework of this investigation. And in case of the motorcycle handlebar, it's also the idea of integrating functionalities, copper wires, for example, finally for the later application. In this case, so we focus on the base structure, which is not just a circular one as it might appear here, but finally was an aerodynamic designed cross section made of the aluminum welding wire AA6063, produced using the WAAM process, and we see such a part structure of the motorcycle handlebar here to the right, which was the basis for the cutting of such specimens, so straight specimens, hollow sections, for the fatigue assessment later on. And the load case is not just an actual one, but a bending load case. Therefore, we set up a fatigue test, which is a combination of simultaneously actual and bending loading. So we have here a lever arm included in an actual fatigue test rig, so that later on we have a maximum stress to the inner side of this specimen, which is again not a circular shape, so that it is pronounced to one specific region. The test setup itself consists of a load frame, load cell, nothing spectacular, except maybe these acoustic emission sensors, which will, but not part of this presentation. We have clamping through the specimen and an hydraulic cylinder for actuation, and the load ratio was so pulsating loading R of equals 0 under constant amplitude loading. Straightforward, the fatigue test results in an SN curve, so more or less in a bending N curve, giving a comparatively high scatter of 1 to 1.7. If we compare it with welding, for example, where we have usually 1 to 1.5 as a reference, it's a little bit higher. The slope in the high cycle fatigue here is around 3.1, and a knee point at close to 1,800,000, evaluated from 13 tests, and the maximum likelihood evaluation in this case. Fracture locations at the region of the highest stresses. So this is the inner part here of the specimen where these cracks then occur and propagating from yeah, more or less the outer surface to the inner part of the specimen. There are not so much internal defects, so that yeah, it is reasonable that crack initiation is from the outer surface, which is not milled or something. So it's the surface as built from the WAAM process. The question then was not just yeah, staying with the SN curve from the force control testing, but also taking a look through the stress-based regime, and therefore the idea was to scan this geometry and use it as an input for a finite element simulation, in this case using Abacus. And as you might see from this procedure, it was not just straightforward scanning and meshing afterwards, but yeah, there were some post-processing necessary using the surface, since the internal phase is not able to scan with an optical scanning system. So using the outer surface and then defining a thickness of the specimen, since the internal surface is not of this importance for fatigue, for the fatigue assessment. And from this, then, yeah, we could perform the finite element load simulation. Before we do this, just a second remark on the thickness. So we see here, for example, two sections of two different specimens, and we can yeah, clearly see that there is no constant thickness from such a process as it is set up right now, at least. So that there are thickness variations, which we have to include, yeah, in our evaluation. And it's not just differing between specimens, but also within one specimen. And therefore, there was a small pre-study focusing on the thickness of such a structure. And what we see is that, okay, from a maximum von Mises stress, in this case from the simulation at a lower thickness, the thickness decrease, the stresses decrease with increasing thickness, and in the range of our application in between 4 to 6 millimeters, the difference in maximum von Mises stresses is around 10%, so that we could yeah, use a reduction factor, which is around 1.1 in this case. With this, we went further to the finite element simulation for every single specimen. So setting the force and the fixed points as it was in the test, and doing the meshing in correlation with the post-processed data. And from this, yeah, we got the results shown over here. So we can take a look through von Mises stresses or maximum principal stresses. In this case, both give us the information on the maximum stressed area of the specimen, which is afterwards then also the crack location in our fatigue test. So there's a good correlation between the numerical simulation here and the fatigue crack location afterwards. This was not just the case for this single specimen, but also for the other specimens we tested. So which is a first good start. But the next idea was, or the next question was, yeah, is it really necessary to have this detailed shape with all these small waves, or do we need to differentiate between a so-called macro geometric shape variation, which you see here, and these really small small waves coming from the WAAM process itself. And therefore smoothing was included, which not just decreases the calculation time, but also gives us the chance to get an idea of the effect of these small waves and the bigger microscopic geometry. And we still see, coming from the ideal model, that with the smooth model, that we still can find the most likely correct location of the specimen. So this is a different specimen compared to the one of the last slide. Yeah, ahead of this simulation, there was also a small study, yeah, giving the relation between a smoothing parameter and the maximum von Mises stress, so that yeah, we set afterwards a smoothing here to a value of 40, which is in the area where this von Mises stress converges yeah, to a certain limit. And yeah, from this, the question is, if we apply this maximum stress to the SN curve, so that we have now, instead of just the moment, the von Mises stress amplitude versus cycles to failure, as a basis, the flat specimen as a reference, and compared to this, the real scanned geometry gives us an idea of the stress concentration of the fatigue pronounced notch. And compared to this, in between is now a little bit hard to see. There is the smoothened one for sure, where we have a lower stress compared to the real scanned geometry. But also what we see is that the scatter from the real geometry to the smoothened one decreases from around 1 to 1.7 to 1.46, which is in the range of for example, welded specimens. Yeah, from this, just a quick conclusion. So we set up this fatigue testing, which was not straightforward, but worked fine. Finally, in this actual bending mode, we had a good correlation between numerical simulation and fatigue track location, and then this investigation on the smoothened specimen geometry versus the real scanned specimen geometry, with the results shown before. Just a quick outlook, if I have the time, which is linked to the presentation before. This was now an assessment based on existing structures. The question afterwards will be, if we have such an CAD model of an ideal geometry, how can we use now our information, which we gather from this hollow section, which we might get from walls, to perform a fatigue assessment in the design stage. And there we come back to this measurement of not just roughness, but surface profiles. And yeah, with this, I would like to thank you, and I'd like to thank the European Commission again for supporting this work, and the project partners of Multifun as well. Thank you.